Those yardsticks.
A major trick today is not writing on this board with chalk or that board with dry erase marker. I don't know if it'll be possible. We're gonna try. Folks, if you're online, I'm sorry, but you only get one half of the boards today because I'm not gonna move the computer that much.
When can we start doing check-in dates? Or what?
I'll send people a calendar today.
Okay. Also, as well, it's gonna be late, freeway entrance just closed.
What is it, the freeway? It says. All right, it's 10:30. You ready?
Mhm.
You ready? You ready? You ready? Okay. So I was looking at what we have left. And we have one more homework. And I don't think you should do it.
What, the special relativity one or the one
Yeah.
that,
Yeah, you have to turn in the one that's due this Thursday,
okay,
but I don't think that I am gonna make you do the special relativity one.
Yeah.
Mostly because what you're about to learn is amazing in and of itself. And you won't have enough time to really process it, to learn how to use it in a meaningful way. So the next two classes, well, I'll talk about them in a few seconds, but. You know, if you want to, you're welcome to do the special relativity homework that is assigned, but it won't give you extra credit or anything else. So I wouldn't recommend doing it unless you've done all of the homework and you're just really bored. The reason for that is this book here is gravity. This is general relativity, an introduction to general relativity. You are about to learn special relativity. Special relativity naturally gives way to general relativity, but it uses one mathematical method that's similar between the two, and that is tensors and Hilbert spaces. And I'm teaching math methods too, so I have decided that you're going to learn general relativity. Because that's a wonderful application of Hilbert spaces, because otherwise they're really boring and they're not that interesting. And so instead, we'll just do special relativity next semester. So this would be like a primer at the like most elite level, and then if you want to take math methods too, you'll learn how to actually do it. Like you'll find out how to model a black hole. That's reasonable? Okay. Okay, so today we are going to learn about this. Reed has already seen it, but you're welcome to have a look at it. On one side is the original Einstein work, and on the other side is the translation, including markups, including his original notes, etc. And this is not a book that I can lend you, but it is a book that you're welcome to look at right now. And what you're going to see in here is you're going to see the culmination of electromagnetism and its impact it has on dynamics. Because what you're about to learn right now is secret knowledge. And I mean this in a very real sense, okay? So people always wonder, well, why did folks get into cults? Why do they want to believe that the earth is flat? So they want to believe that they know something about the world that other people don't. You have now earned, through many years of physics, the opportunity to learn about something that very few people in the world ever understand, ever, okay? Because we're going to talk about what happens when you go really, really, really fast. And you don't know. You have no intuition. You would never have guessed it. And in fact, these folks didn't guess it either. So the first thing that we want to do is we want to take a historical perspective, right? We have all accepted the idea that light moves at a fixed speed. And you just said, sure, whatever, Dr. Grismani, that seems right, right? And no one ever questioned it. But if it were 110 years ago, right? So this book is 111 years old. It makes a statement that the speed of light being constant, which is absolutely insane. Because let's think historically about what we're saying. Wind, air. As I move through the air, okay, the speed at which I'm speaking, right? Like, so imagine for a moment if I have this, I'm running, and I throw it, I add the speeds together, right? So if I were sitting on a train, and you'll notice we're going to do a lot of trains today. If I were sitting on a train and I shot a gun and someone were to measure the speed of that bullet, what would I do? How would I add those velocities? Okay, I'm on a train. And there's a fellow in front of me who I'm trying to shoot on the next train, or maybe they're on a different train and I'm trying to shoot them across the tracks. I fire the gun, I'm doing 100 miles an hour, bullet's gonna go 200 miles an hour. How fast is our combined speed? 300 miles an hour, right? That was correct for 500 years, right? From Galileo until 111 years ago. Okay, because the supposition, the claim, insane as it is that light does not respect this. So if I'm on a train and I'm moving half the speed of light, and I shoot a gun that goes 3/4 the speed of light, how fast should the bullet be going?
Well, we went by our previous logic.
More than the speed of light, right? That's the claim, right? And that's what everyone assumed. So in fact, they tried to look for this because they needed to answer some other questions, and we'll talk about the historical context in a few seconds. But they went to go and measure the speed of light in different directions. You remember this experiment? This is the Michelson-Morley experiment. So what they said was, if I measure the speed of light very precisely, then as the Earth goes around the sun, then what we should see is in some directions, we're going to be going like basically into a headwind in whatever the medium that light goes through. And in some, we'll be going into a tailwind. So just like in a plane, in one direction we'll be going with the wind, and in the other direction we'll be going against. Right? That was the claim. And yet they go and they look at their data, and they find that the speed of light is constant in all directions, all points of the orbit. And they're like, what the fuck? So you might be thinking to yourself, well, that's great. Now they've just proven the speed of light is a constant. But that's not how they interpreted their data. What did they think?
did something wrong.
Well, they knew they did it right because they spent a long time on designing that instrumentation. So they thought that light propagated in a medium, this jelly-like material that was everywhere, that permeated everything, but that was called the ether. Okay. And they thought that there was a preferred direction of the ether. And so as we went through the medium, right, we may chuckle at that now. They're like, what the fuck? That's so stupid, right? But what's the alternative? That the speed of light is a constant? That's garbage. That's hogwash, right? No one believes that. Okay, so instead what they said was, you know what's probably happening? They're like, I got it. The Earth is dragging the ether, just like a rock moving through a stream forms a bow shock. And so there's probably an ether wake that is forming, and that makes the speed of light constant in all directions. That was their interpretation. Right? Hey, I mean, you designed the experiment, you didn't get what you were looking for. If your response at any point is to say, well, all of physics doesn't really make sense, and instead we're going to say the speed of light is constant. No, you have to have a genius mind to think of this, right? Okay, so this is the first part. Now that led to other problems. There was other problems with assuming that there was an ether wake because the aberration of starlight would have implications. So that's something else if you want to look. Okay. So let's talk about relativity for a moment. Because you have already heard of relativity, but you've heard about it in the times of Galileo. So we just said, for example, if I was on a train, and I shot a gun at 100 miles an hour, the train's going 100 miles an hour, bullet goes 200, you add those together, 300. Okay, so I'm on the train, Rolando's on the other train, I'm trying to shoot Rolando, maybe he has a target, not him, he has a target that he's holding, and Kobe's on the ground. Okay, and so Kobe would see all of these events, right? So we would have a clock, and I would be sitting, and I say, okay, class started at 10:30, that's when the gun goes off, bang. You would watch it at 10:30, and the bullet would hit only a few seconds later. This is not very far, right? Okay. And one of the first things about relativity says that if we are in inertial frames, then the physics should be the same, right? So the question is, is there a preferred frame? And one of the questions we have to ask ourselves, are we moving in the universe? Are we the center of the universe? One of the reasons why that's not such a bogus question is because if all the physics looks exactly the same, and we think about it in the context of the way that light travels, then maybe we don't really understand the fundamental physics here. So let me show you an example. Okay. So here you have the canonical example. We have understood dynamics for a long time. But let's remember that right now we're thinking about this is the 1900s, early 1900s, late 1800s. That's whatever it is, what she wants to do. Or I can grab it.
Sorry.
Pitch shape politics. Okay, so let's imagine that it's the late 1800s, and we're learning about Maxwell's laws, and we've written them in this format. Okay, we've learned about E fields, we've learned about B fields, their connections to charges, to currents. We said currents give rise to B fields, and we've said charges give rise to E fields. Is that correct? Good. And then we got a little smart, and we were like, haha, chibbity chibbity. Okay, so here we said, if we write them in this really cool way in terms of the potentials, then I can write them in something called the Lorentz gauge, which relates the vector potential only to the currents, and the electric potential only to the distribution of charge. Okay, all right, cool. So that's like where we stand, and we're thinking about these phenomenon, and it's starting to feel a little uncomfortable. Okay, and here's why. So again, this is Rolando and I, and we are on this tire or on this track, and this is Cody. Okay, this is some machine that produces a perfectly straight B field. This goes right across. Okay, and here's us, and we're just living our lives. We're just enjoying ourselves. And we have some wire loop. It's just a piece of wire. But it is hooked up to a voltmeter. Living our lives, we're going at constant velocity. Now, at constant velocity, you can't tell that you're moving at constant velocity. So instead, we think Kobe is somehow moving backwards. And then we go through this thing. What happens?
I should have been up. Sorry.
For folks online, one, I can hear you, and two, we're looking at figure 12.1. Okay, so what happens when you go through a metal detector at the airport?
Well, it's detected because it's a change in the B field.
So if you change the surface area or the flux through a metal object, you can drive a back EMF. And the back EMF is described in your textbook as equation 713. The EMF is generated as the time rate of change of the magnetic flux through an area. So in this particular circumstance, I perfectly set up this wire loop such that as it goes through the magnetic field, it generates a B field going back in the opposite direction. Right? Okay. So what is doing the work here? So the magnetic force is on the charge, right? If you look at this section and you just think, well, we're sitting here and this thing's moving past us, right? The magnetic loop is at rest. Right? So this would create a back EMF by Faraday's law. And it's due to an electric force, the EVT, right? Okay. But for Kobe, he sees us moving. So he says, no. This is at rest. And this is moving. Therefore, you have a V cross B. So it's a magnetic force. So who's right? Is it an electric force or a magnetic force? Why is Kobe right? Yeah, so the uncomfortable and the annoying answer is they're both right. Okay, so this, for one moment, right, we're saying, well, they have these two things. You have V and you have A. They are different things. They are B, which talks about needles and compasses, and E, which talks about turning on my lights. Okay, these are different things, different forces, and yet, if I view them in different frames, they have the same exact physical response. Okay. So the theory of relativity needs to be introduced again for the purpose of explaining electrodynamics. Okay. All right. So the first two postulates of special relativity are very simple postulates. And if these two things are true, then the whole world changes. Okay, so what's the first one? The principle of relativity. Oh, cool, Mateo. All right, what does that mean? That means that physics looks the same in every inertial reference frame. So what I mean by that is there is no preferred reference frame. Okay, so being on the sun is not better than being on the Earth. This galaxy is not better than the next galaxy, right? Mars is not better than the Earth. Okay. That's the first one. And the second one is that the speed of light is universal. Okay, this is the one, some people will say, well, that's really just like 1A, right? Because the speed of light is universal, then it should be universal everywhere. But really, there's some fundamental physics here that is sort of surprising. If you make the postulate that the speed of light is universal, then you have to change how everything translates, right? Because as I said earlier, if I am shooting a bullet at half the speed of light on a train that's going 3/4 the speed of light, now I can't add them properly because I can never have that number go above 1. Okay, 1 times the speed of light. So I have to create new physics or new geometry in order to describe it. And the implications for that are going to be what we talked about today. Okay. So you've seen Einstein's or Galileo's addition rule. So when Galileo wants to add to velocity, we say Galileo's addition rule. Okay, so let's take the velocity of say 2 objects. The velocity as we perceive it from the ground, Kobe would see from the ground. Let's call that AC. Okay, of the velocity of me shooting the gun, AB, and the velocity of the train, BC. Okay. How do I add those? According to Galileo.
Just that.
Just add. Good. All right. And yet, if this is C, then this is C. Right? That's the claim. Okay, so here's Einstein's law. B AC is going to be equal to V B plus V C. Okay, I haven't done anything yet. Plus 1 plus. So that has some fun design properties. What does that do? When VAB is C. Well, let's ask this 2 different ways. Let's say VAB is very, very, very much less than C. And let's say VBC is very, very much less than C. What do you get?
Just get 0.
You just get 0. So the velocity is 0.
Oh, the total additive.
Total additive is 0?
Oh, wait, B is.
Get the addition.
You just get the normal addition. So when we do new types of physics, they always in the limit have to go back to the original form. So Einstein's addition rule is not valid if in the low velocity limit, it doesn't give you back Galileo. Okay, so that's the first one. It has to give you back Galileo. Good, because we know that Galilean dynamics has worked for a long time, right? This is what we've been using to build everything up until the 1800s. Okay, so the second part. Let's say VAB and VBC are both C. Now what do you get? Do you? You get 1?
C.
Let's do the top.
You just get C.
Ah, you just get C. So if VAB is C and VBC is C, you get 2C on the top. And here I get 1 plus CC over C squared is 1. And 1 plus 1 is 2. And 2 over 2 is 1. Oh, so this is a magic trick. Okay, this is Einstein's addition rule. This allows us to set a speed limit on all things. Now, we say very commonly that C is the speed of light, but it's not. C is the speed that nothing in the universe can go faster than. And it is not restrictive only to light. In fact, any massless particle moves with that speed, C. Any massive particle cannot ever get to that speed. Okay, so
Sorry, massive particle?
any particle with mass,
Okay.
massive. Right, massless particles all move at c
Okay,
in vacuum, all of them. So we think of them commonly as the speed of light because that's what we first assigned it to. But really, we're hitting on a fundamental characterization of the universe itself, which is that nothing, including space itself, can move faster than c. Does that make sense? Okay. Okay, so what is the geometry of relativity? Well, all of this is discussed really beautifully in this book because he performs a series of Gedanken. You know what Gedanken are?
No.
So Einstein was a German Jew, and so he spoke German. So if you are reading very carefully here on the right-hand side, and maybe you're just sort of more impressed with the letters, like, whoa, he wrote so cool. And then you forget to read what he's writing. This is in German. So on the right-hand side, on the right-hand side, you can, I don't know if there's a single line here that I could read. Let's see if I can read the introduction. Oh, I can't, I'm not even gonna try. But anyway, on the right-hand side it's in German. So when he says some phrases like Gedanken, those are naturally carried in. A Gedanken is a thought experiment. So he is going to try and illuminate a new world of physics without you having to leave your house. The reason why this is so incredibly powerful is that you don't even have to move to see that it's true, right? You can write down these thought experiments. You can say, what is the natural logical outcome? Okay. And the first thought experiment is whether or not simultaneity is relative. So you are all right now believing, accurately so, that we are experiencing the same time together in the same place, right? Everything that you understand about the quantum world, everything that you understand about things that are very small or things that are moving very fast, or God forbid, both at the same time, you need to throw away because your intuition will not help you. Okay? So here's the three basic rules of the geometry of special relativity. First, two events that are simultaneous in one inertial frame are not, in general, simultaneous in another. Have you seen this before? Okay, so I have a train, and I'm on the train, and it's moving at a constant velocity. So here's me sitting in the middle of the train. This is the train. And I set up on one side a photometer, and on this side a photometer, and it's moving at a constant velocity. And I flick on the light, and the light goes to both sides, and it hits both photometers, and maybe it emits a small bell noise, and then I hear the bell noise. Okay? Or maybe it stops a stopwatch, right? And it records when that happens. And so sitting on my train, moving at a constant speed, I see them hit both walls at the same side. Right? Everyone agrees that that's true? Okay, it has to be, right? Because there's no way for someone in constant motion to know that they're in constant motion. You only know that you're moving because of accelerations. So for example, when you're turning a corner, you can feel your body getting moved side to side. When you hit a rock, you move up and down, right? Those are accelerations. When they slow down and I speed up, those are accelerations. When you're moving at constant velocity, you can't tell. Similarly, if they were not moving at any velocity, v equals 0, that's also constant, then you shouldn't be able to tell. Okay. So this is moving at constant velocity inside of the train. That's the picture. Here's the photometers, and there's the light. Now, Kobe again, sitting on the outside, doesn't trust any of this garbage, right? And he says, "Nuh-uh, it hit one side before the other." And why is that? Well, because as we're moving to the right, okay, this wall moves closer to the light. And so the combined addition of their two speeds means that this path length was shorter than this one. And so he says, you hit the back wall first. Who's right? Apparently both, okay, and this is correct. They are both right. Because we have to do a number of different things. We have to think about how we measure shit. Okay, so we can't just say, well, I have these measuring sticks and, I placed it from here to here and I knew how long it was. Because that's in a specific reference frame, and that can change if the reference frame begins to move inertially. More importantly, as I use a clock, right? Every clock that exists in nature, whether it's created by your phone, going click, 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 whether it's a natural clock by the atomic degradation of like the clock that is fission, whether it is a pendulum clock, which swings due to the result of gravity, all of these clocks will be subject to the physics under which they exist. Okay, so if I am here, I'm on this train, and I put my clocks and I set them chiming at the same time, right? One on each side, and they're going to record exactly when this light hit it. I would synchronize my two clocks and I would compare them to your clock, and they would not be synchronized. Moving clocks are not necessarily synchronized because moving clocks run slow. This is the principle of time dilation. So if you are moving very fast, your natural clock will move slowly. So what are the implications of that? Let's go back to the idea of a pendulum. Pendulum is still swinging, right? That's like a grandfather clock, right? How can you fuck one of those up? So you put it on the train, grandfather clock swings back and forth, and you see how many swings it had. And when you compare to the same pendulum clock that was claimed to be synchronized at the beginning of this experiment, you will find that it has swung fewer times than the one that is sitting on the ground.
Is this like how an astronaut, if they're twins, one comes back older?
Yeah, so this is the astronaut twin paradox. And with every paradox, what that means is that we don't fully understand the physics. Okay. So the idea for folks who are not familiar is that you have two astronauts, one stays on Earth, one goes off to Beta Centauri for 4.5 light years and then turns around and comes back. And because the person who is traveling at half the speed of light, maybe very close to the speed of light, their clock moves really slow. So they come back and the twin has aged. Is that accurate? Because now the paradox is that there is a preferred frame, right? My whole claim was that in inertial frames, they should all be identical. That's the first rule of special relativity, that there is no preferred frame. So I have some astronaut moving at a constant speed, goes to the nearest star, turns around and comes back, right? And now you can tell the difference between them. So what is wrong with this paradox? Yeah. Who? Right, but I said they move at constant speed.
But they have to turn around.
But they have to turn around. Turning around by definition is right. Okay, so it's a non-inertial frame. So interestingly enough, even for the astronaut whose time is being experienced differently, they will not live a longer life. They will still live 70s, 80 years in their reference frame, right? They are not going to get hit with the wave as soon as they turn around of super aging really quickly. Does that make sense? So instead, they will in fact live much longer than their twin, but that's only because as they are heading this way. I mean, it's gonna be dependent on the path length, right? So if you're heading for a very long time at high speeds, your clocks are not gonna run as quickly. This is the idea of time dilation. Okay. The corollary to that here is that, let's say I have a little clock. Oh, this one here. I didn't even explain this one. This one's straightforward. Okay, I'm on the tram, have a lamp, okay? Light goes straight down. And I just wait, I just see how long it takes, right? Light goes straight down. How long does it take for the light to go straight down?
C or C over, what is it? L. Other way, L over, oh geez. Think of units.
Good. That's how long it takes, right? Okay, that's the interval of time that I found. But Kobe was watching. He doesn't like me very much. He's like, I don't believe it. Okay, the train's moving to the right. So in fact, there is V, right, times that same delta T. So this path length is different than this path length. Right? This is H prime or something. Okay. So in fact, I could write this. I'm not gonna do all of the math here. You can find it in 12.5. But the relationship between the reference frame and the inertial frame, or the frame that is, sorry, not inertial frame, I should be very careful about this. They're both inertial frames. So the relationship between both frames, the one that is moving versus the one that is at rest, okay, is very straightforward. It is that's interesting. So how does that behave? If V is equal to C, what happens?
And there's no difference in the change time.
Look at this carefully. You get 0. Oops, I wrote this in the same place twice. A particle moving at the speed of light does not experience time. The fuck, that's so uncomfortable, right?
The particle even go the speed of light?
Yeah, light's doing it right now. But so are all of the other massless particles. Right? So this again, this is the secret knowledge I was telling you about at the beginning. This is stuff that you've never thought about before and is fundamentally true about the universe. Okay, so this time dilation, very little, right? It's a complicated formula. There's no tensors here. Just 1 minus v squared over c squared. So when v is very small, you get the same time. Right? You don't see time dilation when you have a train go by. No one notices. You have to have sizable v. Okay? V is 1/2 of c. What do you get in here? 1 minus quarter, 3/4, square root of 3 over 2. Right? So now your time gets longer. Make sense? That's right, not longer. 3 over 2 is shorter. Right? The square root of 3 is like 1 point something, and then 2 is larger. Okay. All right. So time dilation, fairly straightforward. How does this one work? This one is the claim that moving objects are shortened. So let's go back into our same train. Handy dandy train. Okay, now I have a light on the back of the train. Okay, so I measure the length of the train and I say, okay, this is like 2L. Okay, and then I put my lamp, over here, and it's gonna have a little light bulb, and I put a beautiful little mirror right here. And I'm just gonna bounce the light off here, and then I'm gonna measure it when it gets back to here. So I have some stopwatch. Click, okay. Boom, I clicked it. And I know how long that that thing is, the train. But you know, I say I'm gonna sell you this train. I've been in it for many, many years. I haven't stopped moving. And it's of length 400 meters. And you measure it and you're like, no, it's not, it's 500 meters. What the fuck are you talking about? No, it's 400 meters. I've measured it many times. I have this wonderful experiment. Okay. But in fact, I find that the moving objects are shortened. This is length contraction. Okay, let's see it happen. So I watch it bounce from here to the other side, right? Straightforward. Let's see if I can write that one out. Okay. So delta t for this person on the left-hand side is just very straightforward. It's 2 times delta x over c, because this is some delta x, right? And then the time it takes over here is delta t. Right? Okay. But it's a little trickier when you're, read and you're trying to measure how long this thing is from the outside. Because now you see the light take off, but it's moved to the right. The light travels a little extra distance before it hits, and then a little bit less on the way back. You see that or not? Okay, because the whole train is now moving to the left. Right. Okay, whole train's moving to the right. So this is some velocity of the train, v, and I want to know what the time is going to be there. So let's write that. The first one is the time it takes to get there. T1 is delta x plus v t1 all over c. Right? So that's adding to the length of the train in one direction. And then on the way back, it's shortened by the fact that the back of the train is rushing to meet you. So I can just rewrite the same thing, but it's going to be like this. Delta x minus v delta t2 over c. Okay, now you can rearrange for delta t1 and delta t2, and you can add them together. Okay, you know exactly what you're going to get. And get this relationship. The time's running slower, right? Okay, it's not something new that we found. But what is the implication for x? So delta x, the distance that's seen in this reference frame, the one that thinks that it's at rest and thinks the whole rest of the world is moving around it, it sees so now let's do that one. So when v is 0, what do we get? What? You just get delta x. It's the same. Good. And when v is c, it's 0. So you get a 0 here, and 1 divided by 0 is blowing up to infinity, getting large, right? Okay. So lengths contract in the direction of motion. Other way around. So if you're moving at the speed of light, okay, you see everything like this, crushed in the direction of motion. Okay. This is Lorentz contraction. Moving objects are shortened. So okay, so I throw this ruler. Right now, we all think of this as roughly being 1 meter. Right? Because I can measure both ends, right? You can look at it, right? But in practice, if it were moving, I'd have to sort of like watch. I'd have to say, okay, how long did it take to go 1 meter? And if it's moving, right? Then I know that there's gonna be time dilation and therefore the length is different. So as this moves by me, it's going to appear to be short. Now, it's really important that it moves by me like this. Because contractions don't occur in the directions that are tangent, perpendicular to the velocity. All right. So if this moves by me at the speed of light, it'll look the same way. But if it moves in this direction, it'll look shortened in this direction, the direction that it's going. Does that make sense? Okay, so here's the fun one, ready? All right. This is a barn. Okay, imagine that this table is a barn. All right, so I can open up this door and I can put the yardstick in, and then I can open up this door and I can take the yardstick out. Right? And if I open up both, I can put the yardstick through the whole thing. Everyone agree? Okay. Now here's the question. Farmer and his daughter have a ladder, a yardstick, that's too big for the barn. They just learned about special relativity, so they say, hey, we got it. Here's what I'll do. I'll just speed the ladder up. It'll contract. And then we'll just open the door, right? You have the door open, Dad, and then I'll just whoop, pop it right in, and then you just close it right after. Right? And because it's contracted, it'll fit. Right? Is that gonna work? Well, Dad
Yes.
gets a little upset. He says, well, hold on a second now. In my reference frame, because you're moving at the speed of light, like that'll contract. But in your reference frame, the barn's gonna contract. Because you won't think that you're moving. Right? And it'll look like the barn's moving at you at the speed of light, so it'll contract. So now we'll never get it in. Right? They're like, hold on. Let's just try it. We'll see what happens, okay? So she runs half the speed of light. Okay, it contracts, okay? She gets it in, it's contracting, and they close the door behind it.
What? She's not moving.
Exactly what happens. So here's the question. Was this yardstick ever really in the barn?
I don't like that question.
Wait. If the barn's contracting and the yardstick's contracting, are they still gonna be like the same? Or like, will they both proportionally change sizes, so it'll never fit anyways?
Yeah, so this is a problem. But there's another problem with the simultaneity of relative events. Right? So as the beginning of the yardstick or the ladder or whatever this analogy is, as it goes through the door, right? As this closes behind it, that's gonna happen in two different people's reference frames, and therefore it's gonna happen at different times. And there is a very likely possibility that the dad will attempt to close the door and it will not be in yet. Does that make sense? And then even if it were in, because of length contractions, right? Let's say we choose the preferred frame of looking at it from the barn's perspective, we see the contraction. You're absolutely right that once it's in, it's gonna expand again once it decelerates. And so therefore it won't be, it'll destroy the barn or destroy the ladder. So this is a wonderful example, and I would 100% have you read this barn and ladder paradox, because it's just as good as I described, but the math is better. Okay, and the reality is that our expectation and our understanding of these events is deeply skewed by our perception that things happen simultaneously, that moving things don't contract, and that our clocks don't change. Okay. Another implication here for moving clocks is lifetimes. So if you imagine for a moment that, let's say a particular particle is going to disintegrate after 10 to the minus 15 seconds. Well, all you got to do is get it close to the speed of light, and it'll last a lot longer. So we can see muons in the lab that live much longer. And in fact, this is one of the major ways that we validate special relativity. Because if you go and you calculate the lifetime of a certain atomic state, And you know, validate it at rest and say, well, it decayed in this many seconds. Good. Now you accelerate the shit out of that thing, right? Get it going half the speed of light. It's gonna suck, right? Because you have to use like a large hadron collider to get it up to those speeds. It's using a tremendous amount of energy. But now you notice that it's lifetime change. Oh, that's because its internal clock, whatever is telling it to decay, is tricked. Its own clock is running slow compared to our clock. This is a very real phenomenon, and we see it all the time in nature. Okay. This one is a lot harder to measure. It's hard to get physical objects going towards the speed of light, right? You can very easily move individual particles and accelerate them to high velocities. It's very hard to move anything macroscopic. And you'll see that in different pieces. Okay. These make sense? This is the basis of special relativity. And this is sort of the intellectual basis for what we're about to learn. And now the rest of it is going to be just amazing. Okay. You believe these entirely, right? All right, so first, let's go back to Galileo for one moment, because now we need to talk about transformations. And I'm not talking about Princess Bride transformations, what was it? The Princess Diaries transformations. We're gonna talk about going from one, you know this one?
No.
You don't know Princess Diaries?
You don't.
Oh my god, canceled right away, out of the class.
I've seen it.
Is like breakout role.
Yeah, she's a normal girl, and then she finds out she's actually a princess.
There you
and
go.
Make her less ugly.
But the only thing they do really is they just take her glasses off, which I feel like as someone who wears glasses, that's fucked up.
And they also make her hair not curly.
Yeah, which is again a different form of fucked up. All right. No social commentary in this class. Okay. So if we are talking about Galileo, and here's this object that I want to describe, then in general, I would use a Cartesian coordinate system, X, Y, Z. Okay. And now let's say I want to translate that reference frame to the right. Because we're on trains, we fucking love trains. Okay. I'm translating that to trains. Okay. So here is the reference frame. Okay, X, Y, Z. There. Okay, and now I want to translate it simply to the right. Okay, and this will be Z prime, this will be Y prime, this will be X prime. Okay, so what's the relationship between Y prime and Y?
It's like the addition of whatever, like,
A number plus,
Is it? Look at it.
like 2, right?
The plus times.
They're the same. Y prime is Y, because it is not in the direction of motion. As you note here, if I am 4 units off in Y, I am 4 units off in Y prime. They are equal. Okay, next one.
it should be equal to these.
This is-
There you go, Z. Okay, I gave you the easy ones first.
this is
This is the trick. I don't like it. Hermione, slow down. All right, let's do the other ones. So let's do X prime over here, Y prime over here, Z prime over here. Uh-oh, what's X prime?
X plus B.
X minus VT.
Okay, good. Is there time? Yeah, there should be time. And let's be nice here, right? Okay, let's call let's say that there's T in this frame and T prime in this frame. Okay, so what's the relationship between T prime and T?
How this to do with the
Remember we're in Galileo's time, right?
Is T and T prime the same?
Yeah, they're the same. Why the hell wouldn't they? Come on, it's not crazy. Time is time. What do you think is gonna change in different frames? Yes, it will. Okay, so that's Galileo. Right? Galileo says as this thing moves around, that you're gonna have, you know, some difference in the coordinate in which you're changing, and otherwise nothing. Right? But Einstein says, nah, it's not true. Okay. So let's draw the same picture. Okay. Here's X, Y, Z at a time T. Okay, and now I'm going to accelerate, or I'm going to move the frame. I should not say accelerate. Here's X prime. Y prime, Z prime at a time T prime. And we have to remember two things here. Okay. What happens to lengths as they move is to the left? What? Smaller. Did anyone write down how they get smaller?
Oh, good. Change it.
Right. So let's call this new factor gamma. Okay. And I'm going to call this gamma 1 over square root of 1 minus v over c quantity squared. Okay, so this is the definition of gamma. I can rewrite what you just said, and I'm just going to use that little piece of information. And I'm going to write that x prime is equal to gamma x minus bt. Now, does that give us back what we expect from the low velocity framework? What is gamma when v is very small? 1. But what does gamma do as v gets larger?
Starts to blow up.
So gamma is a number from 1 going up. So x prime will look like this original one times some other things. So in the moving frame, right? If I think about how to write this one in terms of the other one, then it would be divided by gamma. So in the moving frame, your lengths look normal, but to everyone else, they're going to seem contracted.
That's the movie frame one, or that's?
X is the normal frame.
Yeah.
The moving frame is x prime. And the reason for this is if I want to know what x is, right, in terms of x prime, this is fine. I have to multiply by a number larger than 1. But for someone who's out here who wants to know what everything was in terms of the original frame, to move all that stuff over. So I divide by a number larger than 1, right? Shrinks down the size. That makes sense? Okay. What happens in Y? And Z.
Can you still get through them, you say, because they're not in the direction of motion?
Yep. All done? Ah, shit. Okay, what does T do?
Would it also be affected by gamma?
Yeah, it has to be, right? So what do we know that happens to gamma?
Gamma increases as T increases towards T.
That's what we would expect. We expect gamma to be on the bottom, but in fact, it's not. It's gonna look like this. Okay. All right. So this is the Lorentz transformation. So that was Galileo. No. So these are self-consistent. These allow us to get, using Einstein's addition rule, how velocities add, you can get these motions and the geometry of special relativity. Okay. You'll notice that word over there, Lorentz gauge, that's the same dude. So when we think of special relativity as, one person's tremendous accomplishments, of course, this is an overgeneralization. Because you have to have Lorentz, you have to have Maxwell, you have to have Hilbert in order to do the geometry and the mathematics first. And then for him to say, oh, we can use that mathematics to describe this physical phenomenon, right? Okay.
I have a question.
Yeah.
So if we have a wave then that is like not on an axis or plane as it's moving along, is it going to end up like experiencing more, I guess, relativity, if that makes sense? So when it's not on axis to any sort of plane,
I'm not sure I
in
understand what you're saying here.
like in uniform motion, so
Mhm.
say it's like in the x direction,
Mhm.
and now we have some sort of wave that has components that are going in that motion or in that direction, and then it's also going in like a slightly different direction.
Good.
That's when we have to account for it.
Yeah, very good question. Okay, so what he's saying is, let's say the frame is moving like this, right? And there's some wave, maybe it's a spherical wave. So there are components that move in this direction, and there are components that move tangent to that direction. These off components will not be affected. Only the ones in the direction of motion will be shortened in the reference frame of the moving object. Right? Make sense?
So it's, if you're standing still, you see it, it becomes bigger. You're smaller.
What's that?
So if you're moving.
Yeah.
And it's my reference frame, you become bigger.
I'm heading towards you. I'm moving. I appear shorter to you. But in my reference frame, I don't think that I'm moving. And you appear like you're moving towards me, and therefore you're contracting. Yeah, I know, it hurts. It hurts, but it's okay. Yeah.
So if something were to like move in, like not just in one direction, but like let's say the XY plane,
Mhm.
you would get like something like y prime is equal to gamma y minus bt.
No. Why? Well, because we can just change the coordinate system. And that will always be easier, right? Because these are always, and remember, this is really important, inertial frames. You don't want to do general relativity today. You can do it next semester. You don't want to do it today. Okay? So in a general relativistic frame, you could have components of motion in two directions because you would have an acceleration, which would change the directions. But if you're only going in one direction, let's just make life simple and always orient in the direction of motion. So I know before we had z in the direction of motion and e and b as those components. Well, now we just simply have to say, well, let's always just make x in the direction of motion. Because they'll never have more than motion. Does that make sense? Yeah.
So if you have like a basketball,
Yeah.
does it turn into like an egg basketball then?
Yeah, so there is a really beautiful video called what's it called? I have to look it up. It's what would the world look like if the speed of light was 10 miles per hour? And it conceptualizes physically properly. How and you it's a video game, right? So you like walk around in this video game. Now if you move towards stuff, you get in a combination of the things we haven't talked about so far, you get like red shifting and blue shifting, but you get length contraction. right? So as you accelerate towards something, right, suddenly you get up to moving constant velocity, right? The stuff that is coming towards you is all appearing compressed. Yeah, it's dumb. It's really dumb. Make sense? Okay. Okay, so. So much stuff to get through. I'm gonna, I wrote these in a specific way. I wrote these in a specific way. And it's gonna illuminate something for you that's fundamental, because we're gonna start using tensors to understand how we should really be thinking about physics in the first place. So you have always thought about time as just that thing that you have to keep track of, right? That thing that lets you out of this class, the thing that gets you closer to lunch, right? But in reality, it's a preferred coordinate. So as you can see in the Lorentz gauge, or the Lorentz transformation here, this one here, that changed kind of how we thought. But now time also changes, right? And time is not simply another coordinate. Okay, it's not simply another direction that we can't see. It controls a lot of what we see here, and I'm going to show you why. So 3 of these directions, they are very related to one another, and one of them does something different. And this is the fundamental way that the world works. There are properties called 4 vectors. Notice there's 4 of them. Okay, these 4 vectors describe the world around us. 3 of them will be similar, and 1 will be different. Does anyone know any other 4 vectors? No one's ever heard of 4 vectors, right? Yeah, let's go. This shit's
We covered it.
Okay.
Professor.
All right, so 4 vectors are awesome. You will understand with 4 vectors what E equals MC squared means. Okay. So in order to do that, we have to talk about the structure of spacetime. You ever heard of the structure of spacetime? You drawn a Minkowski diagram or a spacetime diagram?
No.
Do you know what a spacetime diagram is?
No.
Oh, let's go, baby. Okay. All right. So we can write these in a matrix. And we're gonna need to learn a little matrix stuff very quickly. But we probably won't get to E equals MC squared today, but we'll get a little space-time in and be like, oh, that's still cool. Okay. And then to bring you back on Thursday, we'll do E equals MC squared. Okay, so let us write some stuff really quickly. I'm gonna write something like this. This is tensor notation. Oh, I hate it. Okay. And this is CT. And this is beta. And that's B over C. Okay. So I can write this like this: x1 is x, x2 is y, and x3 is z. Okay, this is an array, right? You've all done coding in it before. This is the 0th element of the array. This is the first element. This is the second element. This is the third element. So in fact, I can rewrite this equation here slightly differently. I can say that this is x0, and I'm going to use little bars here so it doesn't get confusing, equals gamma x0 minus beta x1 Don't, right? What the fuck did you write, Chris Money? I hate it. Okay, so here's what I wrote. I wrote y equals y. All right, specifically I wrote y prime equals y. And I wrote z prime equals z. And I moved t from the bottom up to the top. Because I noticed here, I didn't notice this, Minkowski did or someone else. They said, look, here's your t and here's your x. And this new one is a little yummy combination of them. And this new one is a yummy combination of them, right? So I just have that yummy combo up here. So notice the x1s are here. So for this is x, and this is X, and this is X. This is T, and this is T, and this is T. See? Cool, right? Okay. So if you see it that way, then you realize, well, okay, I know how to do this. I'm just gonna apply a matrix to it. So I'm gonna write one 4 vector, which looks like this. Seen vectors before like this?
Yeah.
You've seen this before?
Obviously.
Which one?
Why is it B over C squared? That was V. They both equal beta.
Beta is V over C. And X naught is only CT.
Oh,
Makes sense? So it's not just T, it's CT. Right? If I divided the C over, get everything. Okay. All right, so then I have a matrix. And this matrix is a transformation. This allows me to go from one coordinate system where on the right-hand side, the vectors are X naught, X1, X2, and X3. So this one here, that's my reference frame at rest, and this is the moving reference frame. And all this here in the middle is the transformation matrix. And it's straightforward. Did anyone guess what these two bottoms are?
But like X2 or X2.
Yeah, but what goes here? One, it has to be one, because they are identities, right? So what goes in this bottom row?
Is zero.
Good. And what goes in this?
Zero.
And what goes here? Good. And what goes here? Good. All right, so now the tricky part. So now we want this yummy combo of a little bit of both, right? Right? Okay, so in fact, this is gamma. And this is minus gamma beta. And this is minus gamma beta. And this is gamma. Okay. So you can write this in different ways. Typically, we write this as that. So for the first thing that we're going to talk about, which would be using these types of objects. Well, we've taken dot product before. How do you take a dot product?
Was it trying to both of them and then like sign data?
Yeah, so I'm just gonna take all of the different components of the vector, you know, A times or let's say take the X components, I'm gonna multiply them, and then I'm gonna take the Y components, I'm gonna multiply them, and I'll take the Z components, I'll multiply. So that's the more general way of it, right? So I can do this with any vector. But I can do this also with matrices. So let me give you first the four-dimensional scalar product. Okay, there's a four vector analog to the dot product. So it's not just the sum of the products, rather, the zeroth components have a minus sign. So if I want to do this properly, the first part, A naught, B naught, okay, plus A1, B1, plus A2, B2, plus A3, okay. Now, what have I written here? Well, I can write this as, you know, these are the X naughts. Right, so anything with a 0 would be here in this position, and anything with a 1 would be in this position, anything with a 2 would be in that position. But it doesn't matter which of the products I use, as long as we reserve that the 0 position is always the one associated with time. Right, and then 1, 2, 3, those are your space coordinates. Does that make sense? So if, for example, I had velocities in the XYZ, then these would go here. Right? Okay, that makes sense? Okay. So generally speaking, we can write something that I'm gonna teach you a little bit about the Einstein summation notation. So if you imagine for a moment, I want to write this in a way that doesn't look horrifying. You could say this could be written as a mu bar, representing that it's the transformed one, is going to be equal to the sum of nu equals 0 to 3, so that I go from 0 to 3 of this thing, this matrix. And I'm going to use on the top here, I'm going to use the same one that I want to get out, which is the mu. And on the bottom, I'm going to have the sum over. Okay. Calm down. Okay. Yeah, she got fucked up quick, right? Okay, so let's walk through what the fuck just happened. So this whole thing means this whole thing. This first part here is this first part here. A is a vector. And A is a vector which has mu components, where mu can be 0, 1, 2, 3. So each one of these, this would be A0, this would be A1, this would be A2, and this would be A3. Whereas over here, this is also A, but it's A nu. So this A nu would be A0, A1, A2, A3. Notice the positioning? Notice that this big lambda comes before the vector, right? Because normally what I would do is I would take this thing, multiply it there. Then I take this thing, multiply it there, and then I take this thing, multiply it there, and this thing, and multiply it there. And then I'd sum them all up. Whew. Okay? Is that reasonable? Okay, so I take this whole thing and I multiply it by that and I get this. I take this whole thing and I multiply it by that and I get that. This whole thing, multiply by that, I get that. Okay, so all I've done is I've just reduced it a little bit more. Okay, and in particular, this is a normal sum, right? You would just do the sum, which is the product of the term that has these two values. So if I want to find A1, or let's do these here. I want to find A0. I want to find A3. I want to find A3. If I want to find A3, then I look for the version that is this one, 3. Okay. And I need to sum all of them. So it would be the third line here, because that's lambda 3, and just multiplied by all of these. So this one, this one, this one, they're all 0. Sum them all together, and it's this one. So this one equals that one. You see that? Yes or no? This is matrix multiplication. Right?
Yes.
Okay, so this is just how we write matrix multiplication. Now, we can make it easier and we can make it harder on you. Are you ready? Okay, if you see repeated indexes, see how there's 2 repeated indexes here? That means you should sum over them. And so therefore, we are going to not write this a bunch of times. We're going to assume that you know it. And we're going to write it like this. That is called Einstein summation convention. It's just a time saver. Okay. Unfortunately, we don't get to do space-time yet, but Thursday, we'll discuss whether or not you can move faster than the speed of light, whether or not it's possible to go in and out of a black hole, and then we'll talk about this so-called theory of relativity and how it creates atomic weapons. Okay. Questions, comments, concerns? It's in your book. I haven't created a single piece of new information. No, this is not me. This is all this.
The special relativity input. Do you want the extra?
I mean, if you want to have it for extra credit, you're welcome to, but it's no reason to.